radiation, radioactive particles. People like Wesleyan, who, for reasons that we cannot understand, at any moment may blow up to become somebody new. So they started experimenting with these atoms to see if there was any way they could cause them to explode when they wanted them to, not when they did not want them to. So they did all sorts of different experiments, and then they discovered that there was one type of atom that you could split by hitting them with a neutron. And that was uranium-235. It is an extremely rare form of uranium. Now, here was the problem back in the 1930s. Of all the uranium in the world, 99% of it was uranium-238. 1% of it is uranium-235. That uranium-235, we could split when we wanted it to. The uranium-238 would split when it wanted to. So they realized, if you could split these 235s, they would emit energy. They would give off energy, and that energy could be used to make electricity. That would be cool. Of course, there were people in Germany who were also thinking, we can use that electricity, that energy to make one heck of a bomb. So, two people, Germans and the Americans, were caught in a race in order to figure out a way to enrich uranium. What does it mean to enrich uranium? Okay, so there's 20 of you all. One Wesleyan can be made to split when we want him to. So I take, using a calculator, 1 divided by 20 is 5%. So he, Wesleyan, represents 5% of you all. Keep that in mind, because here was the problem. We needed to change these percentages in order to make a bomb to 15% and 85%. That's what we call enriching uranium. Question: how do we increase the percentage of uranium-235 and decrease the percentage of uranium-238? Let's go back to Wesleyan. He represents 5%. We need to get the number of Wesleyans up to 10% for this room. How do we do that? Nope, there isn't another Wesleyan. Can't do that. What's another way? No, you are Wesleyan. What? Nope. Only Wesleyan will work. We got to, in order for us to make a bomb out of this room, Wesleyan needs to represent 15% of you all. No. Yes. So what happens if we take away Lacey? Now there's 19 of you guys and one of Wesleyan. We've got the percentage up to 5.2%. Let's take Matthew out. 1 divided by 18, 5.6%. That's it. So they had to figure out a way to get rid of 238 and keep 235. Get rid of 238 and keep 235. So we knew the Germans were working on it. So we had to come up with a way, or else if they got the bomb before we did, we were going to be in big poo-poo. So they assigned this job to this general called General Grove, like in Grove Center. Heard of Grove Center? Over there where the There's a church there, right? High Places Church. You know what I'm talking about? Just down where Hibachi Chicken and the other one is? Yeah. That shopping center is named after this general. Okay. So he went through America, different universities that he knew were messing around with radioactive materials. And he found that there were three methods that they had thought of for enriching uranium. Three methods that they had thought of for enriching uranium. So he came back here and he said, okay, well, which one will work? And they said, we don't know. Let's make them all go. So he built a plant in Bethel Valley he called it Y12. Why did they give them code names? Well, what would happen if they were to call it the electromagnetic method for enriching uranium center? Okay, we're in a war. There are German spies everywhere. We would give it away. So in Bethel Valley, the way of enriching uranium that was designed there was called Y12. Now, by this time, they had also discovered another way, and that involves you all, not Westland. They realized that as they were hitting Westland with the neutron, some of you were being hit with the neutron, and you weren't splitting, but you were becoming somebody new. And that somebody new was a man-made element called plutonium. Plutonium. They discovered that, like Westland, plutonium could also be fissioned, could be split. So they built the world's first reactor here in Oak Ridge called X10. And its job was to hit a bunch of you all, not Westland, you all with neutrons in hopes of converting some of you guys into plutonium who could be used for a bomb as well. And then the other method, the final method, was called gaseous diffusion. And they decided to do it in that valley on the way to Kingston. It's called Happy Valley. And that valley was codenamed K25. The problem with K25 is that they thought they could make it work, but they didn't have the technology yet to make it work. So they started building it, sunk billions of dollars in our money, our like modern dollars, billions of dollars, and they weren't even sure that they could ever make it to work. But they did. But it was the end of the war when they finally got it to work. Y12 gave us enough uranium in 2 years to make 2 bombs. The prototype, which was blown up in Nevada, and number 2 was Little Boy. Little Boy. Now, General Grove realized we've got all 3 methods going on at one time. What if the Nazis do find us? May not be a good idea to have all our eggs in one nest. So they built the prototype here. They had a much bigger reactor built all across the country in Washington in order to create plutonium over there. So they made the plutonium for Fat Man. Now, Washington, it was called, the secret city there was called Hanford. Hanford, Washington, and Oak Ridge, we didn't make the bombs. We created the uranium and the plutonium for the bomb. But we didn't make the bombs. The bomb material was shipped down to Los Alamos, who was the 3rd secret city. And there they brought it all together and they actually designed a way of making the uranium go off and the plutonium go off. Yes. Uh-huh. I don't know. Hanford kind of grew up, and I'm not sure that Hanford has that identity of a secret city, but I think Los Alamos has a similar festival. Okay, so after the war, we realized, okay, we can definitely make this into a bomb, but can we use the nuclear reactor to convert it, the energy given off, into electricity? So after the war, we created nuclear reactors thanks to Oak Ridge. So today I want to focus on how a nuclear reactor does its thing. Okay? This video will give you kind of like a summary, and then I'll go into detail. Westland. That is called a chain reaction, and that's critical to understand this. So, what are fission reactions? When you take Westland and you cause him to split into two smaller pieces. How? Not with a remote control, but with a neutron. With a neutron. What's an equation? All right, there's Westland. Right there. And this is my remote control, which caused Westland to split up. He split up into two smaller pieces, and here is something that's very, very important. He created three more remote controls. Three more remote controls came flying out of him when he was split. Why is that important? Because what if there are other Westlands near him? By splitting him, I increases the chances of me splitting other Westlands. It's kind of like dominoes. Have you stacked up dominoes just right so that you topple one of them and they all topple down? Same thing. Same thing. What is so special about 235? It is the only naturally occurring isotope that can be split. Well, what about plutonium? No. Plutonium is man-made. We make plutonium. Right, Jacob? Plutonium is man-made. It's not naturally occurring. Mother Nature did not make plutonium. We made plutonium. So, why do we use nuclear reactors? Why do we use nuclear bombs? Well, think of a stick of dynamite. Nuclear reactor, a million sticks of dynamite. Nuclear reaction will give us a million times more energy than a typical chemical reaction. It's just far more efficient. Actually, I just read The nuclear explosion called the hydrogen bomb that we did in 1952, I think, was more energy. Get one bomb gave off more energy than all the bombs dropped by all the nations in all of World War II. One bomb versus every bomb that was dropped in World War II. Now, do you understand why the Germans and the Americans were racing to get this bomb? What is the unique result? Like I said, Westland, when he splits, will give off 2 or 3 more remote controls, which can be used to split off more of the Westlands. Okay, so here is remote control. Here is Westland. Here are 2 more Westlands. So what happens when he splits up? He releases more neutrons, and those neutrons can be used to split more uranium-235s. What is critical mass? You got to have enough Westlands in one place for this to happen. So critical mass is when you have enough fissionable material for there to be enough of these neutrons bouncing around so it can kind of, it's like you get it started and then it goes off by itself. What's the job of your starter in your car? Just turn on the car. Once the car is turned on, then it goes off by itself, right? It produces its own electricity, which is used to keep it going. All right, so critical mass is enough mass to keep it going. 2 countries that were in a race to figure this out were Germany and the US. Germany and the US. So let's have this teenager try to explain chain reaction to you.
To balance the equation, uranium-236 must emit 3 more neutrons. The chemical equation of the nuclear fission reaction taking place can be represented by this equation. So as you can see from the equation, 1 neutron combines with uranium-235, forming an unstable compound nucleus, uranium-236. This unstable nucleus splits into 2 stable nuclei, barium-141 and krypton-92. In addition to these 2 nuclei, 3 neutrons are also emitted, as well as a high amount of energy, denoted in the equation by Q. Since uranium-236 emits 3 neutrons in the reaction.
All right. So when was the first nuclear reactor built? It was built during World War II. Where was it built? Here in Oak Ridge, Tennessee. It was built to make plutonium for bombs. What is the percentage of nuclear plants in the U.S. that strictly produce electricity? 80%, which means the other 20%'s job is to produce weapons grade plutonium. %. How do most electrical power plants produce electricity? Producing heat that is used to make steam. The resulting steam spins the turbines of giant electrical generators, which produce electricity. I'm going to show you now using a video how this works. Here we go. You might think that this is like super complex. It's not.
Nuclear power plants are thermal power stations which generate electrical energy from heat. They consist of numerous buildings and facilities, the most important of which are as follows. The turbine building houses several turbines as well as the generator necessary for electrical power generation. The containment building where the nuclear reactor is housed is made of meter-thick reinforced concrete. Inside this building, nuclear reactions take place where water is heated up. The cooling tower, which can be as tall as 200 meters, is where hot water is cooled. In order to easily understand the underlying principles, the following is a description of the most important components of a nuclear power plant that uses a pressurized water reactor, PWR. In a reactor pressure vessel, when the nuclear reaction occurs, the associated release of thermal energy takes place. In a pressurized water reactor, as in this case, the reactor pressure vessel stands about 12 meters tall. The walls are about 25 centimeters thick. Inside is where the fuel assemblies can be found. In pressurized water reactors, about 150 such assemblies are installed. A single fuel assembly is composed of many fuel rods.
Okay, so the fuel rods are going to have these teeny tiny little fuel pellets. This little thing that looks like a little piece of chalk that's too small to use is roughly equivalent to 3 barrels of oil, 1 ton of coal, or 17,000 cubic feet of gas. There are millions of these things in a fuel assembly. Pass those around.
A fuel rod is about 5 meters in length and has a diameter of about 23 centimeters. The actual nuclear fuel is found inside of each fuel rod. Small nuclear fuel pellets composed of enriched uranium or plutonium make nuclear fission chain reaction possible. In the fission chain reaction, thermal energy is released. Water is needed in order to absorb the thermal energy and keep the chain reaction going.
Okay, so we're going to get a bunch of Wesleys together in those little fuel pellets. Hit them with neutrons and they get going. So they're going to start producing a lot of energy. You're going to have to cool it down, or else this thing will melt down and possibly explode. So they're going to fill it up with water. This water is going to be under a lot of pressure and not allowed to boil. So the water is going to absorb all that energy and move it. Watch what happens when it moves the heat. 570 degrees.
The heated water is eventually pumped to a heat exchanger, also called steam generator.
Remember, the whole point of the nuclear reactor is to take the energy that was released by Westland and convert it to electricity. Jacob, wake up. Okay, so now you have super hot water that's going to go into these little tubes. Surrounding the tubes will be cool water. Watch what happens. Now, it never touches the second water. Let's call it the second water. The second water is going to heat up and it will be allowed to boil, turn into steam. So now the energy that was in Westland was converted over to the super hot water, and the super hot water is going to turn the heat over to the steam. Ever played around with a tilt-a-whirl or a flywheel? You know, it's like a little flower that when you blow air on it, it spins. Okay, that's what this is right here. It's a big, actually, there's three of them, big, giant flywheels. Does anybody know enough about a car to know what an alternator does? An alternator is going to have an electromagnet running through it, and it has a giant spool of copper wire. And when an electromagnet spins in place in the presence of a spool of copper wire, it creates electricity. They don't know why, but it does. This is a giant alternator. So as this steam turns the flywheels, it turns this alternator, this electromagnet inside the alternator, and the alternator is going to create electricity. This is a 2-story tall alternator, a giant alternator. So now we've converted it into electricity. But that hot water needs to be cooled off. Yeah, you're going to have to cool off that water so it can do its job again. So it's like different loops. How are you going to cool off the water? Well, you better be near a river or a lake because you're going to use river water or lake water to cool it off. You could have one of these giant cooling towers too. So this water right here, where it's red, that will be contaminated with radioactive particles. That's radioactive water. That's dangerous. But it never touches the second loop. So this green here, its job is to get the hot water, the heat from the inner loop, and to create electricity. That water is never in contact with the radioactive water, so it's safe to use. It's safe for us. But you're going to have to cool off this water, so that's the third loop.
the turbine and is not radioactive. The cooling circulation system provides cool water and is used to condense the steam in the stream.
So, how do they differ from nuclear power plants? How do coal-fired plants and gas-fired plants? The fuel. Down the road here, we have, what's it called? Watts Bar? No. What's Melton Hill, coal-fired plant. You've seen the mountains of coal that they burn every day. Okay. Now imagine a large suitcase full of Westlands. That will last you a whole year as opposed to a mountain of coal. I think that mountain of coal over there is just a few weeks worth of coal. Every day they're bringing more and more coal. All right. So what do they burn? They burn coal. Some centers will burn natural gas. Some will burn oil. The whole job is to create energy in order to heat up water so that it turns into steam, and then the steam turns the big giant flywheel, which creates the electricity. So the difference between a nuclear power plant and Melton Hill is just the fuel that's used. And a nuclear power plant is potentially more dangerous. How does the fuel used for coal-fired plants compare? Well, think of it this way. Tons of coal. Small, that's per day. A small amount of fuel per year. The fuel is in the shape of these teeny tiny little pellets that I showed you. How many of these things are there? How many? There might be 10 million pellets in the fuel assembly of a working nuclear reactor. But it's only going to be about 3% Westlands. What does that mean? That means a nuclear explosion cannot occur in a nuclear reactor. Like Hiroshima and Nagasaki, not possible. Why? Because you need 15%, at least 15% to get it up for there to be an explosion like that. And in a nuclear reactor, you're going to have anywhere from 3 to 6%. So bad things can happen in a nuclear reactor. A mushroom cloud is not one of them. So take out your cell phones a second and take a picture of this because you'll need it for your notes, for your worksheet, and for the test. So let's review. This is where you're going to find the Westlands. That's where you're going to find the fuel pellets. That's where the energy is produced. That's where your nuclear explosions are happening. These are called control rods. They're very good at absorbing remote controls, neutrons. So the reaction is too hot. You're a little concerned. You lower the control rods. They get in between the fuel rods and they'll suck up the neutrons and stop the reaction. When the Fukushima earthquake occurred, the first thing they did in all four reactors was lower the control rods in order to stop the reaction. The reaction was stopped. Unfortunately, those fuel rods and that water is still plenty hot, and that's what caused the explosion. All right, so hot water runs through and is cooled off when it comes in contact with the nice cool water. This cool water is turned into steam, and that steam turns a big giant flywheel, which creates electricity. But you got to cool it off because it needs to be water again by the time it comes back here. So you're going to pump in nice cool water from the lake or river in order to cool off the hot water, the steam, in order for this to happen again. So dangerous, dangerous water, safe water, safe water. Actually, the environmentalists will complain that this water is too clean because in order to use it, they have to super clean it and they have to take out all the nutrients that plants and animals use. So when they return it back to the river or the lake, it's too clean. So nuclear power is good. Those of you who are concerned about climate change, doesn't produce any carbon dioxide, and it doesn't pollute the water. The only thing it does produce is nuclear waste that has to be stored. But what's Oak Ridge for? Storing nuclear waste. We'll talk about it. What are control rods made up of? Boron or cadmium? Boron or cadmium. What do? They absorb neutrons. They absorb neutrons. All right, here's a picture. You can see down here, that's where the fuel rods are, and these are the control rods. So they go in and they fit in between the fuel rods. How is a reactor cooled? By water under great pressure. The water is under so much pressure that it cannot boil. The super hot water will then heat another batch of water into steam. We protect this whole thing with concrete walls that are 2 to 4 meters thick. That's about 15 feet thick, folks. 15 feet thick walls.